Okay, so today we are going to talk about fragment processing, which is the last step to enhance the image or to make certain corrections in the fragments that pass, the fragments that are uh, found after rasterizing a triangle or a line. Okay, so here one of the most important steps that we are going to do is called depth buffer test. So if you have a triangle that is in front of another triangle, uh, the triangle at the back, its fragments should not be used to update the pixel color. So that's one thing. So fragments, basically, fragment is a pixel to be, or a potential pixel. That's what a fragment is. In rasterization last week, for example, I mean, not last week, on Tuesday, on rasterization, these are, for example, triangle fragments, these grid cells, as you can see. Okay, for our purposes, I mean, if there was a single triangle, that will be our pixels that we would color. But as I said, if the pixel is the final thing that we see on the image, that's why these are called fragments. These are, as you can see, fragments of triangles. This triangle is composed of 1, 4, 10, 16 in total, I guess, if I didn't count incorrectly. 16 fragments. 16 fragments comprise this triangle, and fragment processing is the pipeline step, and which may be composed of multiple steps to to compute color for these, or to add some effects to these, to disable them, to blend them. So there may be blending. If, for example, you can handle transparent stuff here by blending them with different things. So that's the fragment processing stage. Now, my plan is to go over all of these slides today, and next week on Tuesday we are going to start talking about OpenGL. GPU, we are going to talk about the GPU architecture, OpenGL basics, and how we can use the existing pipeline, the forward rendering pipeline, the default pipeline in OpenGL to send our triangles and rasterize and visualize them. Hopefully I'm going to show you some examples. And also, we are going to start learning a new language named GLSL, which we can write that. I showed you some pieces of codes in GLSL, which is very similar to the C programming language. And then we are going to write these small programs in GLSL. So that will be the topic of the last 4 weeks of this course. Okay, so we are at the 10th week right now. We will have 4 weeks left after this. We'll have 4 weeks left after this class today. All right, so the previous stages, sometimes they're called the vertex pipeline. Rasterization creates this set of fragments. We have talked about rasterization. The rest of the pipeline, which operates on these fragments that we have found on these small triangle pixels, is called the fragment pipeline. And it's also comprised of several operations, which maybe we are going to see, for example, color computation could be done at the fragment stage. And I showed you a website at the beginning of the course, if you remember, the shadertoys.com, I think. Let me see. So shadertoy.com. So this is actually, there are different shaders. If you look at this one, so this is really a nice fractal type of thing, which is like cutout fractal. So what you're seeing here is that, look at this code. So there's a rotation code. Actually, you're familiar with this code, right? I mean, rotation, it gets an angle, cosine of the angle, sine of the angle, mat 2 by 2. So what it's doing is this rotation, I think, is done of these fractals parts, is cosine minus sine cos. So I think it's given in column major order. So distance, fractal, plane, main distance function, normal function, to color, to gray, main image. So this is actually, it computes color for each of the pixels. So it's a fragment shader that we see here. So we will, and this is written in that language GLSL, in which these vectors or functions like normalize are default functions, max, dot product. There is smooth step function, which is also a nice function which you can use to interpolate between certain things. There's I didn't know that. So the fract, I think, is a function that this person wrote. No, I think it's some kind of a fraction function. I don't know the all of the functions available in GLSL, but this is done in fragment processing stage. So this is a code which is part of the fragment processing pipeline that you can write to generate these nice looking images. As you can see, it's interactive. I can rotate it, so it's running on my GPU at the moment at 60 frames per second. It's very fast. I don't know how many. Yeah, the resolution of the image is also small. Maybe that's why it's fast. It's a small image, but if you make it larger, you can still get nice performance. So there, you can take a look at. There are several thousands of examples here. There are nice tutorials also on different fragments, fragment shader examples. So with some nice mathematical functions, you can get really nice looking images. Okay, so let's go ahead and continue with this. At the end result of fragment process is the update of the corresponding locations in the frame buffer. Frame buffer is the image that we have on the. So frame buffer is sent to your monitor, which has an API, some hardware's API, which reads this frame buffer and updates your screen every certain number of every 1/60 seconds, for example. So we did. So if you look at the general overall pipeline again, we started with our vertices in our virtual world. We model, view, projection, transform them, and then we rasterize them. This is the fragment pipeline where the frame buffer is updated, and the frame buffer actually is composed of several sub-buffers. The image that we see on the screen is the color buffer, which we are mostly interested in most of the time. So the frame buffer is, the color buffer is what we see on the screen. There is depth buffer, which we don't see, but which is used extensively for these depth tests. Depth buffer algorithm, which tests which objects are in front of which objects are at the back. So the closest object at each pixel is maintained in this depth buffer. And there's also stencil buffer, which is optionally used to count certain things. As I said, sometimes cut certain parts of stencil buffer can be used to mask certain parts of the image and only render to, for example, to a circular region. Or you have a rectangular frame buffer, but if you want to render something only on a circular region, you can do, for example, a scissors test type of thing by using the stencil buffer. You can mask out certain regions of your frame buffer and not allow update in them. So stencil buffer have different uses. So as you can see, the whole fragment buffer may be very complicated. It's many stages. This is OpenGL handling of the fragment pipeline. So a fragment or a sample and its associated data. Associated data, maybe it's the depth of the fragment, the color of the fragment may be computed before, or normal vectors, whatever is passed as input to this fragment processing stage is the associated data with that fragment. Sometimes that associated data comes automatically as an interpolated value of the vertex pipeline. So in the vertex pipeline, you compute color for vertices. They are in the rasterization stage. We do the interpolation. We have seen how we can do interpolate attributes along the surface of triangles or along the line. This is done automatically by the GPU. We don't do that interpolation part manually when we write our vertex shaders or fragment shaders, but that associated data comes to us as input, and we can do tests like pixel ownership tests. Who owns this? Which triangle is belongs to this one? I don't know the details of all the steps of this, like scissors test, multi-sample fragment operation, stencil test, depth buffer test. This is the most important part. You can do occlusion queries to make occlusion culling. For example, you can at this point, when after it's rasterized, it's interesting why you want to do occlusion query. You can do occlusion query for when you're rendering a scene in a very low detailed version. So it's maybe at the pixel level, the occlusion queries are at the pixel level, but you can use a certain, sometimes you run the entire pipeline for a scene which is much simplified, which the user is not going to see anyway, and you write the resulting frame buffer to some other file. Is an intermediate step. So when we are generating an image, sometimes you may be doing multiple passes in the background in which the user is not even aware of these multiple passes. In one of these passes, for example, you run your occlusion queries for only the bounding boxes, for example, which is going to be a very fast. That pipeline is going to be processed very fast. And after that, for example, or for objects that do not pass occlusion query, in the more detailed rendering pass, in the second rendering pass, what you can do is you can then just throw out objects that do not pass this occlusion query in the first pass. Also, there's an algorithm named shadow mapping algorithm, which, for example, we are going to see that algorithm in this class, which renders the entire scene from a point of view of the light source, as if it's a really nice algorithm. I mean, think about this. If the camera was exactly at the light source, if we have a spotlight lighting a scene, if your camera is there, will you see any shadows in the scene? No, right? I mean, if you have the exact same field of view and exact same vision of a light, you don't get any shadows, because whatever you're seeing, the light rays also see those points, which means that light rays reach those points. There will be no shadow. Okay, so we first render the entire scene from the point of view of the light source, which will give us certain information which fragment the light sees is the information that we want to capture with this render. And that render actually is its results. The only results that we need are in the depth buffer. It's like we are maintaining what is the distance of the closest object that the light source sees in this scene, which is projected onto this pixel. And by using this information, in the second run, where we are actually going to render our scene, we can make this question saying that when we have a fragment that maps, which is the closest fragment in our image from a different point of view, this time from the point of view of the camera, we ask this question: was this fragment viewed from the point of view of the light source? Was that so how you do that is a little bit complicated, but we are going to go into details. But basically what you do is you get that fragment's XYZ value, you just multiply it with the model view projection matrix of the light source's point of view. You get its pixel coordinate, which also gives you its depth. You compare this depth with the previous depth you have saved while you were rendering from the point of light source, and you compare these two. If they're equal to each other, it means that, oh, that's the fragment that the light source saw, so there is no shadow. But if you get some smaller value in that exact location that from the light source's point of view in your saved depth buffer, it means that the object is in shadow, the fragment is in shadow. So this is how we are going to add shadows to our scenes with the shadow mapping algorithm, in which this entire step, as you can see, is run once to just get the depth values. So when we're getting the depth values, for example, we can run our then that depth buffer and that rendering from the light sources perspective, the user does not see that at all. You can actually turn on and off whether you're going to do the frame, send the frame buffer to the screen or to some offline data matrix that you're going to maintain in memory. Is entirely up to you. So the in this two pass, by the way, if you have multiple light sources in the scene, you have to have one pass for each of those light sources. So that's one of the advantages of this shadow mapping algorithm. As I said, we are going to talk about these details later in the upcoming weeks, but I just want to show you that these you may have multiple passes. So some of these boxes may be active in one pass that the user does not see the output. Blending is composing of multiple effects like fog effects, or you can blend different colors together for this fragment. Conversion to different color systems, dithering, logicop. I don't know what, I mean, I know what dithering is, but it's usually about black and white images to get like grayscale effect by just using black and white colors together with some variation. This is what I know about dithering, but I don't know how it's used here. But it's composed of multiple steps. You don't need to memorize any of these steps, just to show you that fragment processing can be complicated. So now here are the details of these different boxes actually. So pixel ownership test. Does the renderer OpenGL has the ownership of the current frame buffer pixel? Well, this happens, for example, when we want to, consider this pixel, which is actually, there's another window in the frame buffer, which is in our the screen that is on top of the OpenGL window, which means that that pixel is not owned by OpenGL. These pixels are owned by other windows, so I think pixel ownership test does that automatically, so that whatever we have in this frame buffer, we don't directly update the monitor's frame buffer at that region. So these pixels do not belong to us, do not update that, because there's another window on top of us. So as you can see, there are operating system related, some of these queries are operating system related to know which processes cover which parts of the screen. This is the OpenGL drawing context we have. Sometimes it may be covered by other parts of the screen. Scissor test is a per fragment operation that discards fragments outside a certain rectangular region. So you can actually, this is like masking out. There's a function in OpenGL, GL scissor, which you can use to just render to a certain portion. Okay, so this is just for cutting out certain parts of the screen. This is different from clipping because it's done on the image space only, and it is an additional thing that you do, not inside the canonical view volume, if you require such a thing. Okay, again, you can render different parts of this image at different passes by using different scissor tests to get different effects if you want, for example. I haven't used GL scissor in my life at all, by the way, so these are some non-standard to get some effect type of functionalities that are provided for you. There are multi-sample operations. Each frame buffers sometimes pixel may contain multiple samples. Sometimes we have, again, this is an advanced type of operation that we didn't do. For example, we can have, instead of, we treated every pixel as a single pixel, which is at the center. What if each pixel was actually like, there were 4 points inside a pixel, which you can make inside-outside tests, for example, where you're doing rasterization. For example, for this pixel, 1 point is inside, 3 of them are outside. So based on that, you can give a shade of red to this one. So you can actually perform this anti-aliasing that I told you before to get a triangle which is going to look more smooth at the boundaries. So this is called multi-sample operations. In ray tracing also can be done by shooting multiple rays to random locations within a pixel. Yeah, I think yeah there it can be used for other. It's not only for anti-aliasing. You're right. It can be used for light bleeding, for example, for smoother shadows, or for yeah for light getting effects to other places. It can be done, I think. Uh, so this is just provided for you as some advanced functionality in the Fragment pipeline, and it can be used for these other operations. Yeah, it is possible, but as I said, we are not going to go into much details of these. You just know that there are different steps that you can apply at different stages of the pipeline, and some of those we are going to use, like the stencil test. We are going to use the stencil testing uh, in another shadow algorithm, which is called shadow volumes. We are going to shadow volume algorithm. We are going to see two algorithms for generating shadows in OpenGL. Shadow mapping, I briefly described how it works, and shadow volume algorithm is also going to it requires multiple passes, and in certain passes it just checks how many, for example, surfaces the count of faces that are rendered at that pixel. So we will be using as a count buffer. So it's similar to, in this regard, I mean, if you look at the use of the stencil test, in this example, it's very similar to Caesar test, but the Caesar test is just for a rectangular area. Stencil buffer gives you a much more flexibility because you have an entire buffer. You can make you can turn on and off pixel level different parts of your buffer to get different rendering effects. For example, you can have a stencil buffer which looks like this checkerboard pattern, and you can have a stencil test that set in such a way that for those parts, for example, which are black, do not render. If it's one, render. For example, you can have test like this, and this triangle, the original triangle, which is texture map like this, after the stencil buffer testing, you can render a triangle that looks like this, like certain parts, certain bricks are cut out or taken out. So you can have interesting effects by just working in this fragment space. For example, to achieve such a thing, you would probably need to have your virtual objects subdivided into multiple triangles, or I mean, you would increase the complexity of your scene's geometry to achieve something like this, if you really want to cut out these parts. But doing this at the image space is much more efficient, and since very simple binary tests are done, while when this is rendered out, this becomes something very fast, very efficient. So this is, we are going to see the use stencil test, as I said, in shadow volumes algorithm. So here, sometimes depth and stencil buffers are saved together on the same image, because the depth value is not three-dimensional. We have three channels, right? RGB value. Actually, usually frame buffers are composed of 4 channels. Even the color buffer, there's RGBA. The fourth value is the alpha, RGB alpha, which shows the transparency level of a pixel. So it's actually, most of the frame buffers we have are 32 bits, 1 byte per channel, which gives you 32 bits per pixel most of the time. So using all 32 bits for the depth, we could use, I mean, we could have done that. Actually, 4 bytes is just one float number. If we have stored our depth values as float, we could use the entire 32 bits for just the depth information. But usually, typically, for a pixel, the first 3 bytes are used for the depth, and stencil information does not require you. When you're doing the counting, most of the time you just use some binary value to store in the stencil buffer. Stencil buffer requires lower number of bits. So usually 8 bits are used for stencil information, the 24 bits are used for depth information. So yeah, stencil buffer and stencil test can also be used to implement one type of shadowing algorithms. As I said, we'll learn this later. So the shadows you see here of this creature and of the train wagons, carts here are generated by using the shadow volume algorithm. So Doom 3 uses shadow volume algorithm to get these dynamic shadows. By the way, if your shadows are static, you can generate these shadows by what is known as baking those shadows into the textures. So you can pre-process if you have fixed light sources which are at fixed locations, and if they're always going to cast shadows, and the objects are not moving, non-moving objects, the non-moving objects are going to always cast the exact same shadows on every frame. So you can actually pre-compute them and change your textures and use them, or use it as an additional information that updated your textures. But if you have moving objects in your scene, like these creatures, for moving objects like this, getting dynamic shadows is not possible by just, you have to update your shadows at every frame, 60 times at every frame. So getting these dynamic shadows is not easy. So there are algorithms for this. Shadow mapping is one, and shadow volumes is the other algorithm that stencil test will be using that shadow volume algorithm. The most important fragment operation, as I said, is the depth buffer test, which allows objects that are, for example, fragments of this mountain that are behind some of the trees are not used to update the pixel values. This is done with the depth buffer test. We can render these mountains or these trees in any order we want, but if we didn't have the depth buffer algorithm, what we would have to do is, in order to correctly render the scene, we would render objects at back to front order, which is known as the painter's algorithm, because this is what painters do. They start with the background and add objects to the background, starting from the farthest objects first. So first from the mountains and the background scene, and then the final things come afterwards. But this is difficult. I mean, especially when you can use something like the binary space partitioning tree that we have learned earlier. BSP trees could be used. You have to structure your scene with BSP trees. If your camera is moving, you can use the same BSP tree, but you have also moving objects in your scene, then you have to update your BSP tree accordingly. But with the depth buffer algorithm, you don't need to do this sorting at all. You can render your objects in any order. Basically, yeah. This is why I talked about BSP tree, but still BSP trees it's difficult to, there is no total order among these objects, for example. Which one is in front, which one is at the back? Can you sort these objects from back to front order? Red, blue, green? No, green is actually behind red. So this is part, in order to actually have a total order for these objects back to front, you have to chop these objects into pieces. Because partially, so it's in 3 dimensions, they are oriented in such a way that parts of it are behind, parts of it are in front. So in our BSP tree, we have to subdivide them into smaller objects so that we have these order. But as I said, with the depth buffer algorithm, you don't need to worry about any of these things. Any of the chopping of the objects into pieces is not necessary. Because you treat everything pixel by pixel, fragment by fragment. You just check, while you're rendering this fragment, you just check what was the, if you rendered, for example, the green first, it will update certain parts of the frame buffer, and you just need to ask, what is the depth of that fragment? Not depth of the entire object. Depth is something, again, we interpolate along the surface of the object. So the depth of a fragment which updated this pixel's color value last is stored in the depth buffer, and when a new fragment comes, all we need to do is check, is the depth of the new object is smaller than the previous object that has updated this pixel. And if that's so, you update the depth buffer value and you update the color value. Yeah, in depth buffer right now is something really standard, is done automatically, but they were implemented in the early days of the first-person shooter games or other three-dimensional graphics. Quake, they didn't have the depth buffer algorithm. Quake was one of the first games that used painter algorithm by applying BSB trees. So it didn't have the depth buffer test, and they didn't have those high-end graphics cards. So each game level was stored as a huge BSB tree, so it was rendered back to front. And the depth buffer algorithm, I actually mentioned it a couple of times, but here it's written nicely. At each pixel, we keep track of the distance to the closest fragment that has been drawn in a separate buffer. That's called the depth buffer, or sometimes Z buffer. Okay, that's the same thing. Discard fragments that are further away than that distance. Again, when I say discard fragments, again with the assumption of we have all opaque objects. If we have transparent objects, a depth buffer with just a single Z value would not be sufficient. We would need something else. At each of those pixels, we would need an array of, a vector of Z values that have contributed to that pixel. So transparent objects are handled in a different way. But assuming we have opaque objects, we just discard the fragments that are farther away than the current distance in the D buffer. Otherwise, we draw the fragment, update the Z buffer with the Z value of that fragment. So it requires an additional image, which is called the depth buffer or Z buffer. And at the beginning of every frame, the depth buffer is reset to infinity, which is 1.0 in practice, if the depth ranges between 0 and 1.0. So when we're doing these drawings of objects, one thing that is really interesting is that if we are doing it 60 frames per second, at the beginning of every frame, the entire color buffer is erased, the entire depth buffer is erased, refreshed, and everything is done from scratch for every frame that we are generating. This sometimes causes flickering, okay? Because if you see some image, if you turn everything to background color before you actually start drawing new things on them, our eyes are going to get, although you do it very fast, even at 60 frames per second, your eyes are going to catch this clearing, which is going to cause what we call flickering. In order to avoid this flickering, actually each of these depth buffer, the color buffer, they come in two copies, which is this strategy is called double buffering. In double buffering, we all the operations are done on one buffer, one set of buffers, color buffer, depth buffer, and while we display this to the user. When we erase this, we don't actually show this. We then compute the next, while we are computing the next frame buffer, this one stays there. And what we do is we compute the next frame, everything, we paint this one. Instead of, before we erase this one, we switch our monitor screen with the second double buffer instantaneously. So there's at every frame we're swapping between buffers while we're working. After the second buffer is put onto the frame buffer, then we erase it and start working on it, and after it's finished we just plug in the buffer that is ready. So it's just buffer switch between them. We are going to talk about that when we come to OpenGL again, but this is required to avoid flickering, and it's also something very easy to do in OpenGL. You just say, I want to use double buffering, and enable double buffering, and that's it. And at the end of every rendering, you just say swap buffers, and it's done automatically. So it's something very easy to do. But just know that all these buffers, color buffer, depth buffer, practically they come in sets of two. to do this to avoid this flickering effect. So here's an example for depth buffering in which the triangles are, there's at some point the yellow triangle or yellowish greenish triangle is in front of this gray one, and at some certain points the gray one is in front of the yellow one. So initial state is this. We first render the white one. Okay, so the white one I think is parallel, as since its depth are all 5, 5, 5, 5, 5, 5. The gray one is parallel to xy plane, but the green one is not parallel. Its depth values along the surface are changing. So when we render this, the frame buffer looks like this. And the second one, this greenish one, when we render it, this part is farther away, as you can see, 777. This part is closest to us. The lower left corner of this green one is closest to us. Its depth value is 2. By the way, these are just given as integers to make it as a nice, understandable example. And these are all 777, as you can see. And the values change along the surface smoothly, as you can see. So what will happen is that these parts that are 7, we just check them whether, while we are rendering it with this, which parts are going to be updated. We are going to just take a look at the value and compare it with 5. If it's, by the way, also when they're equal to each other, you can decide on whether it has to overwrite or not, because they have exactly the same z value. I think you can just say whatever's come later, you can just overwrite if you have the same z value. But for the parts that have larger z values like 7, they are not updated, as you can see. 7 or 6, these parts are not updated. These parts are updated as 7 because they were infinity. These are the parts in which this gray triangle did not touch. So we can update it like this. So this is done pixel by pixel, fragment by fragment. We can correctly render objects that are behind are correctly occluded with this method. There is the depth range, which is between 0 and 1 by default, could be scaled to different values. There's an OpenGL, there's a function called GL depth range in which you give 2 z values, z min and z max. That the default one is between 0 and 1. So what GL depth range is doing, so in GL viewport, we can change the width and height of these things. So the GL depth range, we can also play with the depth of this. I don't see the practical use of this. I mean, if you're other than it's just doing scaling. I mean, if you're just comparing your z values between each other, you can just keep the default depth range. Okay. Again, this is a function I have never used in my life. We talked about z fighting when we were talking about this projection transformations, the near and far planes. The range between near and far plane defines makes the z fighting more drastic or less apparent. Here they are compressed to range 0 and 1 after this near far transformation in projection transformation and viewport transformation. Okay, so with a limited precision in the depth buffer, fragment values that are close in depth may get mapped to the same z value. So that was as you can see here, the z values, they are between 80 and 100. All these z values are mapped to very close places here. If you have objects that are close to each other, the depth buffer test may get confused which one is going to overwrite the pixels, which one are not. So we can get these interesting effects, interesting results like this, which is not desired if really the green one was in front. Okay, so one thing to get rid of this situation is either you change your near-far plane ratio to a more reasonable. Don't make your far plane very far, make it closer to the near plane, or you can change the or you can make this object a little bit in front of the other object. Do not give it just 0.1 z larger. If you really want to have this green rectangle in front of the red rectangle, increase the distance between them a little bit farther. I mean, just make the distance between them larger. So here's an example of Z fighting in a real scene, I think, in Unity or some other rendering tool. As you can see, we have some texture that is mapped onto this one, in which OpenGL is not able to identify which one is in front, which one is behind easily. Yeah, this is repeating the same thing I said. The separation of the far and near place should be kept as small as possible. Alternatively, we can use a floating point depth buffer, which is supported in modern GPUs. You can maybe set the depth buffer size that you're going to be using. I mean, each pixel you can give it a different type to use in the depth buffer values. I don't know whether double precision is possible, but we can check that. Yeah, also GL polygon offset, as I said, you can make if you really want the green rectangle to be in front of the red rectangle, you can just use this GL polygon offset function on the green rectangle to push or pull polygons a little to avoid Z fighting. And the final thing here, where we are going to talk about our occlusion queries for occlusion culling. We mentioned this again. If you remember this figure, it was about our clipping and culling slides. At the end, we had this. Our goal was to completely remove all of the triangles of the bunny if it's in front of this blue triangle. We want the bunny is occluded by the blue triangle, so we want to cull it entirely. So OpenGL supports occlusion queries to assist in occlusion culling, but here, as I said, you need two rendering passes. Occlusion culling happens at the pixel level, so if you're rendering the entire bunny before the occlusion culling, there is no need to do that. So by a fast rendering count, we first need a fast rendering pass. Maybe instead of rendering the entire bunny, we use a low resolution version of it, or a bounding box surrounding the bunny is rendered only. Imagine instead of having these 10,000 triangles, you just first render this single triangle and a cube, which may be composed of 12 triangles only. It counts how many pixels of the tested object will be rendered with this occlusion query, and it's commonly used in games. And this was the hidden slide at the end of that clipping and culling slides. It's a complicated sequence of steps. We are not going to implement this in any assignment, just we want to give you for information how this can be done. We first, in that rendering pass, which is the fast one, we disable rendering to screen. So we don't want the users to see the simplified version of the scene. So by setting the color mask of all channels to false and disable writing to depth buffer, we just want to test against but don't update the depth buffer. We issue a query, GL occlusion query. We render here, this is the critical part, we render the object's bounding box only because we don't want to spend too much time on rendering all those tens of thousands of triangles. It will only do depth testing. Pixels that pass depth testing will not be rendered on screen because rendering and depth writing were enabled, and the query. And then here we count visible pixels here. We enable, during this occlusion query part, we enable rendering to screen. So everything is enabled back. We get the result of number of visible pixels. If the number of visible pixels is greater than 0, if there was something visible for that object. By the way, while we're rendering, this is for a single object. So when that single object was not rendered, if the count, for example, of that pixel was 0, that object was not visible at all. It was occluded by some other triangle. So if the number of pixels is, if it was visible, we render the complete object, otherwise we just completely cull the object. So if you, this is not too detailed, if you don't, I just went very quickly over these things, because we don't see how each of these steps will be done specifically in which OpenGL functions, but just know that occlusion culling can be done in two passes, in which the first pass renders a bounding box of this, and if this bounding box is never rendered, this is counted with the occlusion query, and no pixel of this bounding box is rendered, then the entire bunny will be invisible. So completely take the bunny out in the actual rendering pass. Another fragment processing operation is blending, alpha blending, which is for the effect of these transparent objects. The new objects can be blended with the existing frame buffer, existing contents of the color buffer for a variety of effects. Without blending, we get this, all of the objects are opaque. So if you want this red sphere to be transparent, we can have its fragments while we are running its fragments, while we're rendering it. We can use a fragment shader in which the computed colors are going to be blended with existing colors of the already rendered object. So this is called alpha blending, and it can be done again at the fragment processing stage. There is this conversion from different color formats, this sRGB conversion. The fragment values are converted to sRGB color space before being written to the frame buffer, and this main reason is for gamma correction. So without the gamma correction, the scene looks like this. After gamma correction, it's like equalizing the histogram of these color range. With the gamma correction, you get this effect. And it's also questionable which one is better. I mean, this is more like this is also good, but there are certain dark regions which we cannot see the details of this avatar here. At the back of the avatar, it's more visible. It's more like an HDR type of thing here, but it's just gamma correction. It just linearizes certain things. Okay, so in summary, at the end of the pipeline, input vertices with connectivity information end up populating certain regions of the frame buffer after rasterization, and the entire pipeline can be implemented only on the software by CPU, or parts of it are entirely on GPU, which when you use the either programmable pipeline or the default pipeline, or sometimes you use both CPU and GPU to do certain operations to get your final fragment, final frame buffer image. Okay, so here, so this concludes our fragment processing part. We haven't seen much new things, but the depth buffer idea and all the other generating different effects, masking certain parts of things. So stencil buffer is used for counting. You can use different parts of this pipeline steps, fragment processing pipeline can be used to achieve different effects. Now, starting with next week, we are going to see some real applications in which we are going to write some OpenGL programs, codes to actually change part of this fragment pipeline, vertex pipeline, to get ourselves some applications which run very fast on the GPU, real time, and that will be the last part of this course. Okay, so that's it from me for today. Next week our topic will be, I'm going to put this next week's slides also on AutoClass, and they will be about GPUs and OpenGL Basic. So 1 week GPU OpenGL Basic, which is this one, graphics, hardware, and OpenGL. We're going to talk about the GPU architecture, why it is fast, and things like that. And then we're going to talk about OpenGL a little bit. And then OpenGL shaders. We are going to write our own vertex and fragment processing stages with OpenGL programmable shaders, and how we can have textures and different frame buffers in OpenGL. That will be 1 week after that. And with that, we are going to also talk about shadow mapping and shadow volumes algorithm. And we are going to finish the course. I mean, we have these 4 weeks of classes left. So we have finished fragment processing, and we have 4 weeks of classes left in the semester anyway. So we will finish with curves, which is how to have, instead of triangles and lines, can we have smooth curved surfaces implemented? How can we use polynomials in 2D or 3D to have effects like a flag, which is some arbitrary, like cloth with a different shape like this. So we are going to conclude the course with that. All right, so that's it from me for today. If you don't have any questions, have a nice weekend, everyone. I'm going to stop recording now.